What if all the ice on Earth were to vanish, leaving the continents and oceans exposed in ways they have not been for millions of years? Imagine the glaciers of Greenland receding, the colossal ice sheets of Antarctica reduced to liquid, and the frozen peaks of mountain ranges across the globe disappearing into rivers and lakes. Ice, in its vast variety and distribution, is more than a passive layer of frozen water. It is a regulator of climate, a reservoir of fresh water, and a sculptor of the physical landscape. Across the polar regions, ice acts as a reflective shield, bouncing sunlight back into space, stabilizing temperatures, and maintaining the balance of ecosystems that have adapted to millennia of frozen conditions. The disappearance of these frozen masses would trigger a cascade of environmental transformations, some immediate and measurable, others unfolding slowly over centuries. Antarctica alone contains approximately 26.5 million cubic kilometers of ice, a volume sufficient to raise global sea levels by nearly 58 meters if fully melted. Greenland adds another 2.85 million cubic kilometers, translating to around 7.4 meters of potential sea level rise. Beyond these continental giants, smaller glaciers and ice caps around the world, from the Andes to the Himalayas, store an additional 170,000 cubic kilometers of ice. Polar sea ice, though seasonal and thinner, contributes to oceanic albedo effects, influencing the absorption of solar radiation. Together, the planet's ice reserves cover about 10% of the Earth's surface, yet they hold roughly 68% of all fresh water. The distribution is uneven, the thickness variable, and the response to warming climates differs between regions. But the underlying principle remains. These frozen reserves are integral to the hydrological and climatic equilibrium of Earth. The mechanics of ice melt involve the interplay of temperature, sunlight, and oceanic heat. Ice absorbs and reflects energy differently depending on its surface composition, density, and age. Fresh snowfall reflects more sunlight, while older, compacted ice becomes darker and absorbs more energy, accelerating melting. The ocean exerts pressure on coastal ice shelves, warming beneath the frozen surface and gradually destabilizing massive ice formations. Greenhouse gases, such as carbon dioxide and methane, trap heat within the atmosphere, pushing temperatures beyond thresholds at which ice remains stable. The retreat of glaciers is not uniform. While some shrink rapidly, others respond more slowly due to topography, thickness, and latitude. Yet the cumulative effect of sustained warming is inexorable. The loss of ice mass is measured in both seasonal fluctuations and long-term decline, and the consequences are global. As ice melts, sea levels rise. Coastal plains that have hosted human settlements for millennia would be submerged. Cities redefined by waterlines rather than streets. A rise of just 1 meter affects tens of millions of people. The complete melting of Antarctic and Greenland ice sheets would inundate entire nations. Island chains, low-lying deltas, and river mouths would disappear beneath the waves, while inland seas could form in formerly dry basins. The shifting water mass would alter the flow of oceans, changing currents that distribute heat and nutrients around the planet. Salinity patterns would adjust, affecting the density-driven circulation that drives deep water formation. These shifts have ramifications for global climate systems, as the transfer of thermal energy between equator and poles governs weather patterns, storm formation, and the distribution of rainfall across continents. Ecosystems respond to ice melt with both fragility and resilience. Polar species, adapted to extreme cold and seasonal cycles, face immediate threats as habitats vanish. Penguins, reliant on sea ice for breeding and feeding, encounter shrinking platforms for nesting and reduced access to krill, a foundational food source. Polar bears, dependent on hunting seals across frozen seas, must traverse longer distances or face starvation. Glacial meltwater feeds rivers that sustain inland flora and fauna. Its reduction disrupts freshwater availability for both wildlife and human populations. Alpine ecosystems experience similar pressures as high-altitude glaciers provide meltwater during dry seasons, supporting plants, insects, and herbivores that have evolved to depend on a stable hydrological regime. The loss of ice triggers feedback loops that accelerate environmental change. As ice recedes, darker land and ocean surfaces absorb more sunlight, increasing warming and further melting the remaining ice. Methane trapped in permafrost and subglacial sediments may be released, intensifying greenhouse effects. Shifts in temperature gradients alter atmospheric circulation, potentially increasing the frequency and intensity of storms, droughts, and heat waves. The interconnectedness of ice, atmosphere, and ocean means that local changes reverberate globally. The disappearance of a single ice sheet is not a contained event, but a signal with planetary reach. Human societies face profound consequences. Coastal populations are most directly affected, with potential displacement on an unprecedented scale. Freshwater scarcity could intensify as glacial reservoirs disappear, affecting agriculture and energy production. Trade and infrastructure suffer as ports, roads, and urban zones are submerged or destabilized. Economic systems, insurance models, and food supply chains must adapt to the transformed landscape. In regions reliant on glacier-fed rivers, hydroelectric power and irrigation may falter, forcing communities to seek alternative energy and water sources. The global population, intricately linked to stable climates and reliable fresh water, would be compelled to adjust both physically and socially to a new planetary reality. Geophysical consequences accompany these environmental and societal changes. The removal of vast ice masses reduces pressure on underlying crustal regions, resulting in post-glacial rebound, where land rises slowly, sometimes triggering earthquakes or volcanic activity in formerly suppressed zones. River courses and sediment transport adapt to new water volumes, reshaping valleys, deltas, and coastal features. Redistribution of mass can even affect the rotation and gravitational balance of the Earth subtly, illustrating that ice is not merely a surface phenomenon, but a component of planetary mechanics. Over centuries and millennia, the disappearance of ice would redefine Earth's appearance. New coastlines would emerge, some continents slightly larger as land previously under ice becomes habitable, while low-lying regions vanish beneath rising seas. Biomes would shift as temperature and moisture regimes change. Tundra and boreal forests might give way to temperate or even semi-arid zones. Ocean chemistry could be altered by increased freshwater input, affecting salinity, nutrient cycling, and the marine food web. The long-term consequence is a planet recognizable in shape, but altered in function, where ecosystems, climates, and human societies must recalibrate in response to the loss of frozen reservoirs that once dominated the landscape. Scientific observation provides a record of these processes. Ice cores extracted from Greenland and Antarctica reveal layers of snowfall dating back hundreds of thousands of years. preserving evidence of atmospheric composition, temperature, and volcanic activity. Satellite measurements track ice mass and movement in near real time, confirming trends of thinning and retreat. Climate models project future scenarios with varying degrees of ice loss, offering estimates of sea level rise, temperature change, and hydrological impacts. Each data point reinforces the understanding that ice is both the sentinel and regulator of global climate, and its disappearance is neither abstract nor distant. As the planet adapts to this transformation, reflection on human and planetary perspective becomes inevitable. The scale of change challenges the imagination. Entire species and landscapes are confronted with new realities, and humanity must weigh mitigation against adaptation. Scientific awareness offers insight and caution, yet the physical processes continue, indifferent to human concern. In this quiet, factual consideration, there is both awe and gravity. Ice, often overlooked in daily life, is revealed as a silent architect of Earth's climate, oceans, and ecosystems. Its potential absence underscores the delicate balance of forces that sustain life and shape the world. In contemplating a world without ice, one returns to the initial question, now enriched with understanding. What would happen if all ice on Earth melts? The answer is multifaceted, encompassing oceans that rise, landscapes that shift, species that struggle, and human societies that adjust. Yet, within this contemplation, there is a quiet recognition of the intricate interdependence of Earth's systems, a reminder of the profound influence of frozen water, and a reflective awareness of the temporality and fragility inherent in planetary processes. The story of ice, its presence, and its potential loss is ultimately the story of Earth itself, observed with care, measured with precision, and acknowledged with quiet respect. In Antarctica, the sheer scale of ice dominates the southern continent, shaping both geography and climate. The East Antarctic ice sheet, stretching across millions of square kilometers, holds the majority of the continent's frozen water in a relatively stable state, though even it experiences gradual change at the margins. The West Antarctic ice sheet, by contrast, rests on bedrock below sea level in many places, rendering it highly susceptible to ocean warming. As warmer currents intrude beneath floating ice shelves, basal melting accelerates, thinning the ice and destabilizing the structure. Ice streams, vast rivers of ice flowing toward the sea, respond to these changes, increasing their velocity and delivering greater volumes of ice into the ocean. Should the entirety of Antarctica's ice melt, coastlines worldwide would be transformed, submerging low-lying nations, inundating river deltas, and redrawing the map of continents. The contribution of Antarctica alone to global sea level rise is staggering, dwarfing the effects of all other ice sources combined. Greenland presents a similar yet distinct scenario. Its ice sheet covers roughly 1.7 million square kilometers, and though smaller than Antarctica, it is comparatively more vulnerable due to its position in the northern hemisphere and proximity to warmer ocean currents. Melting in Greenland is already contributing measurably to sea level rise, as surface meltwater channels and glacial carving introduce enormous volumes of fresh water into surrounding seas. The albedo effect here is critical. As the bright white surface of the ice sheet darkens from melting and debris accumulation, more sunlight is absorbed, accelerating warming in a self-reinforcing cycle. The implications extend beyond local geography. As freshwater input can disrupt the North Atlantic thermohaline circulation, influencing climate patterns across Europe, North America, and beyond. Mountain glaciers, though individually smaller than continental ice sheets, collectively exert a profound influence on freshwater systems. The Himalayas, often referred to as the Third Pole, host thousands of glaciers feeding the rivers of Asia, including the Ganges, Brahmaputra, Yangtze, and Indus. Seasonal meltwater supports billions of people downstream, sustaining agriculture, industry, and daily life. A complete melting of these glaciers would initially flood river systems, then result in long-term reductions of freshwater availability, compromising food security and water supply for densely populated regions. Similar processes occur in the Andes, Alps, Rockies, and Caucasus, where glacial retreat has already been documented through both field measurements and satellite imaging. In each mountain range, the interplay between ice, elevation, and climate creates a unique set of outcomes. Yet all contribute to the global picture of hydrological change. Polar sea ice, though thinner and seasonal, plays a different but equally vital role. The Arctic Ocean, covered by sea ice that expands in winter and retreats in summer, affects regional temperatures by reflecting solar radiation and insulating the ocean from the atmosphere. As the ice diminishes, darker ocean surfaces absorb more heat, further warming the Arctic and amplifying the retreat. This Arctic amplification has consequences far beyond the poles. Jet streams may shift, altering storm tracks and precipitation patterns across mid-latitude continents. The disappearance of sea ice also opens new maritime routes and alters marine ecosystems, affecting species such as seals, walruses, and fish populations that depend on the seasonal ice cover. The melting of ice has a direct impact on oceanic circulation, which is essential for distributing heat and nutrients globally. Large influxes of fresh water from melting glaciers and ice sheets reduce seawater salinity, affecting density gradients that drive the thermohaline circulation. Changes in this deep ocean conveyor can slow or redirect currents like the Gulf Stream, modifying climate regimes in Europe, Africa, and the Americas. Coastal upwelling regions, critical for marine productivity, may be altered, impacting fisheries and the broader food web. Ocean stratification could increase, reducing vertical mixing and affecting the distribution of oxygen and nutrients, with consequences for phytoplankton growth, the base of marine ecosystems. Terrestrial ecosystems respond in diverse ways to ice loss. In the Arctic tundra, permafrost contains vast amounts of organic material, frozen for millennia. As ice melts and permafrost thaws, microbial activity accelerates, releasing carbon dioxide and methane, reinforcing global warming. Vegetation zones shift northward as soil temperatures rise, altering habitats for herbivores such as caribou and predators like wolves. Coastal wetlands and estuaries, fed by glacial rivers, may be submerged or salinized, affecting migratory birds, amphibians, and fisheries. In mid-latitude regions, rivers once fed by snowmelt may experience seasonal scarcity, stressing both wild and cultivated ecosystems, reshaping landscapes and species distributions over decades. Human infrastructure is acutely vulnerable to the consequences of ice loss. Cities built along river deltas or coastal plains face inundation, necessitating relocation, fortification, or abandonment. Ports and harbors must adapt to rising tides, while urban drainage and sewage systems confront increased pressure from both flooding and altered precipitation. Agriculture, dependent on stable seasonal water availability, must contend with disrupted irrigation and altered growing seasons. Hydroelectric power, reliant on meltwater flow, may decline initially after glacial retreat, challenging energy production. The economic ramifications ripple through industries, trade, and government planning, emphasizing the interconnectedness of ice, water, and human society. Geophysical responses to ice loss extend to the mechanics of the planet itself. The removal of vast ice masses reduces downward pressure on the lithosphere, causing post-glacial rebound, which slowly elevates land previously compressed by ice. This uplift can destabilize regional fault systems, potentially triggering earthquakes or even volcanic eruptions in formerly suppressed zones. Rivers carve new channels, sediment patterns shift, and coastal geomorphology adjusts as land masses rise, while seas encroach elsewhere. Even the Earth's rotation and gravitational balance may experience subtle, measurable changes as mass is redistributed across the globe. Ice, though often perceived as inert, is an active agent in the structural dynamics of the planet. As meltwater flows into oceans, chemical and thermal properties are altered. Freshwater input decreases salinity in localized regions, influencing marine species adapted to specific salt concentrations. Temperature changes affect breeding cycles, migration patterns, and predator-prey relationships in the ocean. Nutrient transport may be disrupted, impacting phytoplankton productivity and, consequently, the entire marine food web. Coastal upwelling, which supports fisheries, may weaken or shift, reducing the abundance of commercially important fish and affecting human food supply. These cascading effects illustrate the tight coupling of ice, water, chemistry, and life, where a change in one domain propagates through multiple systems. Throughout history, ice cores provide insight into past climate events, revealing cycles of warming and cooling. Layered snowfall preserves dust, gases, and isotopic ratios, enabling reconstruction of atmospheric conditions over hundreds of thousands of years. These records show that even relatively small changes in global temperature can produce dramatic shifts in ice extent, sea level, and ecological distribution. Satellite monitoring complements historical data, tracking ice mass, movement, and surface temperature with precision. By integrating these measurements, scientists can model potential outcomes of complete ice melt, offering projections that range from decades-long sequences of glacial retreat to multi-century transformations of coastlines, climates, and ecosystems. The contemplation of a world without ice reveals the scope of its influence on planetary stability. From stabilizing temperature gradients to supplying fresh water and shaping habitats, ice is a regulator of both the physical and biological environment. Its loss would not be isolated, but would ripple through oceans, atmosphere, and land. Human awareness, while critical, is challenged by the scale and pace of change. Societies may adapt through engineering, relocation, and policy, yet the fundamental shifts in climate, water distribution, and ecological balance will demand ongoing adjustment. Observing these processes offers a perspective on the interconnectedness of Earth's systems and the magnitude of frozen water as a structural and ecological cornerstone. As the planet responds, reflection deepens. The disappearance of ice is not merely a numerical calculation of sea level rise or glacial retreat. It is a transformation of environments, ecosystems, and human lifeways. The quiet influence of ice, often unnoticed in daily experience, emerges as a defining element in Earth's stability and habitability. Its potential absence underscores the transience of natural systems, the interdependence of climate, water, and life, and the profound scale of environmental change. In these observations, there is a sense of measured awe, a recognition that ice, in both its presence and absence, shapes the very fabric of the world. In the Arctic tundra and boreal forests, the retreat of ice exposes soils that have been frozen for millennia, initiating profound ecological shifts. As permafrost thaws, the release of trapped organic carbon becomes a significant contributor to atmospheric greenhouse gases. Microbial activity accelerates, producing both carbon dioxide and methane, which enhance global warming in a reinforcing loop. The disappearance of sea ice extends the growing season for tundra vegetation, allowing shrubs and grasses to encroach on areas previously dominated by mosses and lichens. This change alters the habitat for herbivores such as caribou and musk oxen, while predators, including wolves and Arctic foxes, must adapt to shifts in prey availability. The ecological cascade reaches aquatic systems as well, with altered river flow patterns and increased sedimentation affecting fish species that rely on specific spawning conditions. Glacial meltwater serves as a crucial freshwater source for thousands of rivers, feeding millions of people and countless ecosystems downstream. In Asia, the Himalayas' retreating glaciers threaten the perennial flow of rivers such as the Indus, Ganges, and Brahmaputra. Seasonal flooding may initially increase as melting accelerates, followed by long-term reductions in flow that compromise irrigation, hydroelectric power generation, and drinking water availability. In South America, the Andes glaciers feed rivers critical for agriculture, including rice, maize, and wheat cultivation. Alpine communities, reliant on meltwater for municipal supply, face diminishing resources. Similar patterns appear in Europe and North America, where retreating mountain glaciers reshape river regimes, affecting both urban centers and natural wetlands. As ice vanishes, the interconnectedness of climate and human society becomes increasingly apparent. Rising sea levels inundate coastal regions, threatening dense population centers in South and Southeast Asia, parts of the United States, Europe, and Africa. Low-lying deltas such as the Mekong, Ganges, Brahmaputra, and Nile could be substantially submerged, displacing tens of millions of people. The economic costs of relocation, infrastructure modification, and loss of arable land are staggering. Fisheries are affected as altered currents and nutrient availability impact marine productivity. Agriculture suffers from both saltwater intrusion into soils and decreased fresh water for irrigation. Energy production is challenged as hydroelectric dams, reliant on glacial runoff, experience variability, while thermal power stations must contend with warmer water for cooling. Oceanic systems respond dynamically to the addition of massive freshwater volumes from ice melt. Thermohaline circulation, driven by differences in temperature and salinity, may slow or reroute, altering the distribution of heat across the planet. The North Atlantic, for example, depends on dense, salty water sinking in the Labrador and Greenland seas to drive the Atlantic meridional overturning circulation. An influx of fresh water could reduce density, weakening this engine and potentially cooling Europe despite overall global warming. Shifts in ocean currents also influence the upwelling of nutrient-rich waters, affecting fisheries and marine biodiversity. Coral reefs, highly sensitive to temperature and salinity changes, may experience accelerated bleaching and die-off, further disrupting marine ecosystems that millions rely on for food. The geophysical impact of ice melt is equally significant. Post-glacial rebound lifts land masses formerly compressed by ice sheets, altering topography over centuries. This uplift can destabilize tectonic structures, inducing earthquakes or volcanic activity in previously suppressed regions. Rivers change course, carving new channels as sediment deposition patterns shift. Coastal morphology adapts as land rises in some areas, while sea level rise erodes other regions. Even the redistribution of mass affects Earth's rotation and gravitational field subtly, demonstrating that ice is a dynamic component of planetary mechanics, intimately linked with the structural balance of the globe. Feedback mechanisms exacerbate these changes. The albedo effect diminishes as reflective ice surfaces are replaced with darker land or ocean, absorbing more solar energy and accelerating warming. Thawing permafrost releases methane, a potent greenhouse gas, amplifying temperature increases. Reduced ice cover alters atmospheric circulation, potentially shifting jet streams and changing the intensity and frequency of storms. These interactions underscore the complexity of Earth's systems, revealing that ice is not merely a static layer, but a regulator that maintains climate stability and ecological balance. Human adaptation, how these transformations is both immediate and long-term. Coastal cities must consider protective infrastructure, such as levees, seawalls, and flood barriers. Yet, these measures are limited by scale and cost. Relocation and migration may become necessary for populations in low-lying regions. Agricultural practices must shift to accommodate changing water availability and altered growing seasons. Energy systems may require diversification to compensate for fluctuating hydroelectric and thermoelectric output. Urban planning, economic strategy, and international cooperation all face new challenges as the planet adapts to diminished ice reserves. In each case, the dependency of human society on the natural regulatory function of ice becomes unmistakably clear. The disappearance of mountain and polar ice also reshapes biodiversity on a global scale. Species with narrow climatic tolerances, particularly cold-adapted organisms, face immediate existential threats. Penguins in Antarctica lose breeding grounds as sea ice retreats. Polar bears in the Arctic see hunting ranges diminish. Alpine flora and fauna adapted to glacially fed ecosystems struggle to survive as snowfields vanish. Lower-lying ecosystems, reliant on consistent meltwater, confront new drought conditions and shifts in nutrient supply. Even migratory species, which time reproduction and feeding to seasonal glacial cycles, may encounter mismatches in timing, affecting survival rates and population stability. These transformations underscore the profound interconnectedness of ice, climate, and life. As global temperatures rise and ice continues to melt, climatologists project shifts in weather patterns worldwide. Monsoon systems, dependent on temperature and pressure gradients influenced by glacial presence, may weaken or shift geographically, altering precipitation regimes for billions of people. Droughts may intensify in regions formerly buffered by glacial runoff, while flooding could increase in areas experiencing sudden glacial meltwater surges. Storm systems may draw greater intensity from warmer oceans, and polar jet streams could become more erratic. The loss of ice thus reverberates through every atmospheric layer, reshaping weather dynamics from tropical zones to polar regions, affecting both natural and human systems. Freshwater resources, intimately linked with ice, become increasingly variable and stressed. Glacial reservoirs that buffer seasonal rainfall provide stability for irrigation, hydropower, and municipal use. As glaciers retreat, initial surges in river flow may be followed by sustained reductions, especially during dry seasons. Communities that have relied on these predictable sources may face scarcity, impacting food production, industrial processes, and potable water access. International river basins, shared among multiple nations, may encounter new political pressures as water availability fluctuates, highlighting the socio-political dimension of ice melt. Oceanic ecosystems undergo profound change in response to altered salinity, temperature, and nutrient fluxes. Phytoplankton populations, the foundation of the marine food web, are highly sensitive to these variables, and shifts in abundance cascade through trophic levels. Fish populations that sustain commercial fisheries may migrate or decline, affecting livelihoods and global food security. Marine mammals, seabirds, and benthic communities adjust to changing prey distribution, sometimes successfully, sometimes not. The integrated response of oceanic life demonstrates that ice, even when distant from tropical oceans, exerts control over planetary biological rhythms. Scientific observation provides the evidence necessary to understand and anticipate these changes. Ice cores, satellite imagery, ground surveys, and climate modeling offer insight into past and present ice dynamics. Each method reinforces the interconnections among ice, climate, hydrology, and ecosystems, allowing predictions of how ice loss will propagate through natural and human systems. The precision of modern observation ensures that projections are not speculative, but grounded in measurable trends and historical patterns. These studies highlight both the scale of potential change and the necessity of informed human response. As the narrative unfolds, a broader perspective emerges. The presence of ice stabilizes temperature, supports freshwater supply, regulates oceanic circulation, and provides habitat for diverse life forms. Its potential absence underscores the fragile balance inherent in Earth systems. Human societies, reliant on these processes, are forced to confront both immediate challenges and long-term adaptations. Ecological, climatic, and geophysical transformations are intertwined, emphasizing that ice is not merely frozen water, but a central element in the functioning of the planet. In reflecting on a world without ice, the mind returns to the initial question with a clearer understanding. The melting of all ice on Earth would trigger a chain of cascading effects: rising seas, shifting climates, stressed ecosystems, altered ocean chemistry, and societal upheaval. The planet would emerge recognizable in structure, but transformed in function. A world reshaped by the loss of frozen reservoirs that have persisted for millions of years. Observation, measurement, and reflection reveal both the scale of these changes and the intricate dependence of life and human activity on the presence of ice. In quiet contemplation, there is an acknowledgement of the profound role ice plays in sustaining balance, mediating climate, and supporting the interwoven fabric of life. Beyond the polar extremes and major mountain ranges, ice exists in smaller glaciers scattered across virtually every continent, each contributing to local hydrology and climate regulation. The Alps, for example, provide fresh water to much of Central Europe through rivers such as the Rhine, Rhone, and Po. Retreating glaciers here lead to initially higher runoff, followed by significant reductions over decades, altering agriculture, hydroelectric output, and urban water supply. The Andes, stretching along South America's western edge, contain glaciers that feed rivers critical to communities and ecosystems in Peru, Chile, and Argentina. These glaciers buffer seasonal variability, providing water during dry periods. Their disappearance threatens both highland settlements and the vast lowland agricultural zones dependent on regulated flow. In North America, the Rockies and Alaska's glaciers contribute to river systems like the Columbia, Yukon, and Colorado, which support cities, farmland, and hydroelectric infrastructure. Seasonal melting ensures predictable water delivery. Without ice, flows become erratic, creating periods of both flood and drought. Similarly, in Asia, the Pamirs and Tian Shan supply rivers that are lifelines for millions. Even modest glaciers in these ranges play a crucial role in stabilizing regional climate, moderating temperature extremes, and maintaining ecological balance. The cumulative effect of global glacial loss is not simply additive but multiplicative, influencing hydrological cycles worldwide and magnifying stress on human and natural systems. As ice retreats, the redistribution of water and mass affects ocean dynamics. Large-scale melting reduces salinity and density in critical regions, impacting thermohaline circulation that regulates global heat transport. For instance, freshwater influx from Greenland can weaken the North Atlantic circulation, slowing the Gulf Stream and potentially cooling Europe despite overall planetary warming. Similar processes in the Southern Ocean affect the Antarctic circumpolar current, which connects ocean basins and distributes nutrients. Changes in these currents influence weather, sea surface temperature, and marine productivity, with cascading effects on fish populations, coral reefs, and the entire marine food web. Ocean acidification, exacerbated by CO2 absorption, interacts with temperature and salinity changes to further stress marine life. Coastal and marine ecosystems experience compounding effects from ice loss. Mangroves and salt marshes, already sensitive to sea level rise, face submersion and salinity intrusion. Coral reefs, reliant on stable temperatures, suffer increased bleaching events as ocean temperatures rise. Polar marine life, adapted to ice-dependent ecosystems, must adjust or perish. Species like krill, foundational to Antarctic food chains, decline as sea ice diminishes, impacting penguins, seals, and whales. In the Arctic, polar cod populations decrease as sea ice retreats, affecting seals, walruses, and polar bears. These cascading biological impacts highlight the profound dependence of life on ice, where a change in one domain echoes throughout the planetary ecosystem. Terrestrial ecosystems are equally affected. As glaciers retreat, alpine meadows expand, but soil composition and water availability change, impacting endemic species. River-fed wetlands shrink or vanish, affecting birds, amphibians, and fish reliant on seasonal water flow. Forests adjust to new moisture and temperature regimes, with boreal forests encroaching on tundra and temperate forests responding to altered precipitation patterns. In regions formerly covered by permanent snow, soil erosion accelerates, destabilizing slopes and altering river sediment loads. These shifts produce long-term ecological reorganization as species compete, migrate, or decline in response to changing habitat and hydrological conditions. Human societies face profound and multifaceted consequences. Coastal cities, from New York and Miami to Mumbai, Shanghai, and Lagos confront rising seas, storm surges, and flooding. Low-lying island nations risk complete submersion. Agricultural regions experience altered irrigation patterns, soil salinization, and reduced water availability, threatening food security. Hydroelectric systems dependent on glacial runoff lose reliability, while thermal and nuclear power plants struggle with warmer cooling water. Transportation infrastructure, urban planning, and public health systems must adapt to increasingly unpredictable conditions. International relations may be strained as nations compete for freshwater and habitable land, illustrating the global reach of ice melt beyond environmental concerns. Geophysical responses to ice loss continue over centuries. The removal of vast ice masses reduces pressure on the lithosphere, triggering post-glacial rebound. Land previously compressed by kilometers of ice slowly rises, subtly altering local and regional topography. Tectonic stresses adjust, sometimes inducing earthquakes or volcanic activity in previously suppressed zones. River systems adapt, sediment transport shifts, and coastal geomorphology changes as some regions rise while others are submerged. Even Earth's rotation and gravitational distribution experience minor adjustments due to mass redistribution. Ice, though solid and seemingly static, is integral to the dynamic equilibrium of the planet, influencing both surface and structural processes. Feedback loops intensify these transformations. As ice recedes, darker land and ocean surfaces absorb more solar energy, amplifying warming. Thawing permafrost releases stored methane, increasing greenhouse gas concentrations. Changes in temperature gradients modify atmospheric circulation, affecting jet streams and storm intensity. Seasonal patterns shift, with implications for agriculture, water management, and biodiversity. The loss of ice accelerates processes that would otherwise unfold slowly, illustrating the interconnectedness of climate, hydrology, and ecosystems. Scientific observation continues to illuminate these processes. Ice cores provide historical records of atmospheric composition, volcanic activity, and temperature fluctuations over hundreds of thousands of years. Satellite monitoring tracks ice mass, movement, and surface temperature in near real time. These data allow researchers to model future scenarios with increasing accuracy, projecting timelines for ice loss, sea level rise, and ecological impacts. Observations confirm that the disappearance of ice is not a distant theoretical event, but an ongoing phenomenon with measurable consequences, demanding careful study and responsive planning. In contemplating these changes, a reflective perspective emerges. Ice stabilizes global temperatures, supports freshwater supply, regulates oceanic circulation, and sustains biodiversity. Its disappearance represents not just the loss of frozen water, but a transformation of the systems it governs. Human societies, intricately dependent on these processes, face adaptation challenges at unprecedented scales. The planet, reshaped by melting ice, retains its landforms and oceans, yet operates under new climatic, ecological, and hydrological conditions. Observation and analysis reveal both the vulnerability and resilience of life in the face of these transformations. The story of a world without ice is ultimately one of interconnected consequences. Melting glaciers and ice sheets, retreating sea ice, thawing permafrost, and shifting ocean currents collectively redefine climate, ecosystems, and human societies. Sea level rise inundates coastal zones, altering urban and agricultural landscapes. Ecological networks reorganize as species respond to new environmental pressures. Oceanic and atmospheric circulation patterns shift, influencing weather and productivity across continents. Geophysical adjustments reshape landforms over centuries. Each element is part of a dynamic, interdependent system, highlighting the centrality of ice to the stability and function of Earth. Quiet reflection on this scenario underscores the magnitude of ice's role. What may appear as mere frozen water is, in fact, a regulator of planetary climate, a provider of fresh water, a support for ecosystems, and a modulator of geophysical processes. Its absence would ripple through oceans, continents, and atmospheres, affecting every living system and human community. Scientific observation allows us to comprehend the scope and interconnectedness of these effects, fostering both understanding and caution. In contemplating a planet without ice, one appreciates the delicate balance that has allowed life and human society to flourish, and the profound consequences of disrupting that balance. In the long term, the disappearance of ice reshapes continents and coastlines. Low-lying deltas, river mouths, and islands vanish beneath rising seas, while previously glaciated regions, once buried under kilometers of ice, emerge as new land. Post-glacial rebound continues over centuries, lifting former ice beds and altering regional topography. Mountain ranges reveal bedrock and valleys that have been shaped by ice for millennia. Newly exposed landscapes are initially barren, but over time, soils develop through the deposition of wind-blown dust, sediments from retreating glaciers, and decomposed organic material. Vegetation gradually colonizes these areas, creating nascent ecosystems that differ from those that existed before glaciation. The slow transformation illustrates both the destructive and regenerative aspects of ice loss, as land and life adapt to new conditions. Polar ecosystems, once dominated by ice-dependent species, face unprecedented stress. In the Arctic, sea ice reduction diminishes hunting platforms for polar bears and seals, while disrupting migratory patterns for birds such as Arctic terns and geese. The loss of ice algae, which thrive on the underside of sea ice, affects krill populations, cascading through the marine food web and impacting whales, penguins, and fish. In Antarctica, the shrinking Ross and Weddell seas reduce breeding and feeding grounds for penguins, seals, and seabirds. The disappearance of ice shelves removes physical barriers that stabilize glaciers, accelerating ice flow into the ocean and further modifying marine habitats. These polar changes reverberate globally, demonstrating that ice loss is both a local and planetary phenomenon. Mountain ecosystems are similarly transformed. Alpine flora, adapted to glacial meltwater, must migrate to higher elevations or face decline. Fauna, from insects to mammals, adjust to changing water availability and temperature regimes. Glacial lakes form as ice melts, initially increasing freshwater availability, but also creating risks of sudden outburst floods. Downstream, river systems experience altered flow, sediment load, and seasonal timing, affecting agriculture, urban centers, and fisheries. In regions dependent on glacier-fed rivers for irrigation, crop cycles may shift, and water scarcity could become acute. These consequences highlight the integrated nature of ice, water, and human livelihoods across continents. Human adaptation to ice loss becomes both a necessity and a challenge. Coastal populations confront rising seas, storm surges, and changing tidal patterns. Cities invest in protective infrastructure, such as seawalls, levees, and flood barriers. But these solutions are limited by cost, scale, and environmental impact. Relocation may be necessary for millions, creating social, economic, and political pressures. Agricultural systems must adjust to altered water supply and growing conditions, implementing irrigation management, crop diversification, and water conservation techniques. Energy systems reliant on hydropower must adapt, while thermal and nuclear plants contend with higher water temperatures and reduced flow. The interdependence of human systems with ice and water highlights the global scale of adaptation required. Climatic consequences of ice disappearance extend beyond local or regional changes. Atmospheric circulation patterns shift as polar temperature gradients diminish, affecting jet streams and storm trajectories. Monsoon systems in Asia, Africa, and the Americas may weaken or shift geographically, altering precipitation patterns for billions of people. Droughts could intensify in regions previously buffered by glacial runoff, while extreme rainfall and flooding may increase elsewhere. Ocean currents, weakened or redirected by freshwater influx, change heat distribution across the globe, influencing both coastal and inland climates. The complex interplay of ice, atmosphere, and ocean ensures that the removal of ice triggers cascading effects on weather, climate stability, and ecosystem health worldwide. Freshwater systems experience dramatic alterations. Glacial meltwater, a critical source of river flow and groundwater recharge, initially floods rivers before declining as ice reserves diminish. Seasonal predictability is lost, complicating irrigation, energy generation, and urban water supply. In major river basins like the Ganges, Mekong, and Colorado, water availability becomes more variable, stressing agricultural and industrial systems. Disputes over transboundary water rights may intensify as nations face reduced flow from shared rivers. These changes demonstrate the societal dimensions of ice loss, emphasizing that water security is intimately connected to frozen reserves across the planet. Marine ecosystems dependent on stable temperatures, salinity, and nutrient flux adjust to altered conditions. Phytoplankton growth, influenced by sunlight, temperature, and nutrient availability, may decline or shift geographically, affecting the base of the food web. Fish species migrate toward favorable conditions, altering fisheries and global food supply. Marine mammals and seabirds adjust feeding patterns or face population declines. Coral reefs experience thermal stress and acidification, resulting in bleaching and mortality. The interconnectedness of ice, ocean chemistry, and life highlights that the disappearance of ice is not isolated, but has far-reaching implications for global biodiversity. Societies observe and respond to these changes through scientific measurement and planning. Ice cores provide historical records of climate and atmospheric composition, allowing understanding of long-term trends. Satellite monitoring tracks ice mass, movement, and surface temperature with precision, providing data for climate models. Predictive models project timelines for ice loss, sea level rise, and ecological consequences, informing policy, urban planning, and disaster preparedness. These efforts underscore the value of observation, measurement, and analysis in comprehending and adapting to the consequences of ice loss. Reflection on a world without ice reveals the profound influence of frozen water on Earth's stability and habitability. Ice regulates temperature, supplies fresh water, supports biodiversity, and shapes both oceans and landforms. Its loss triggers a cascade of interconnected effects, from rising seas and altered climate to ecosystem disruption and human adaptation challenges. Scientific observation allows understanding, yet the physical processes continue independently of human action. In this quiet contemplation, one perceives both the vulnerability of planetary systems and the resilience inherent in life, adapting to changing conditions while highlighting the importance of ice in maintaining global equilibrium. Ultimately, imagining a planet devoid of ice brings a sense of perspective. The frozen expanses of Antarctica, Greenland, mountain glaciers, and sea ice, often overlooked in daily life, are central to the regulation of climate, water, and ecosystems. Their disappearance would redefine coastlines, climate patterns, species distribution, and human settlements. Observing the scale and interconnectedness of these changes cultivates awareness of the delicate balance sustaining life on Earth. In the absence of ice, the planet would be transformed yet continue, shaped by forces both immense and subtle, reminding humanity of the profound influence of frozen water on the rhythms of life. The story of ice, its presence and potential absence, is ultimately the story of Earth itself. From the deep interior of ice sheets to the smallest glaciers, from the polar seas to mountain streams, frozen water orchestrates the movement of heat, water, and life. Its loss would cascade through continents and oceans, reshaping climates, ecosystems, and human societies in profound and lasting ways. Quietly, relentlessly, ice has maintained balance for millennia. Its disappearance would signal a fundamental transformation, one measured not only in meters of sea level rise or temperature change, but in the reorganization of life, the reshaping of landscapes, and the adaptation of human civilization. Observing this, one is left with both awe and reflective understanding, contemplating the subtle yet immense role ice plays in sustaining the planet's intricate systems. As the ice continues to disappear, feedback loops intensify, producing cascading changes across the planet. Reduced albedo from vanishing ice surfaces allows more solar radiation to be absorbed by land and ocean, accelerating regional warming. In the Arctic, the retreat of sea ice contributes to polar amplification, raising temperatures faster than the global average and triggering permafrost thaw. This thaw releases vast quantities of carbon dioxide and methane, amplifying greenhouse gas concentrations and reinforcing atmospheric warming. Such interactions illustrate the self-reinforcing nature of ice loss, where initial changes propagate through multiple environmental systems, magnifying their effects over decades and centuries. Regional climates respond in complex ways to ice reduction. Monsoon systems, which rely on thermal contrasts and atmospheric circulation influenced by glacial and polar ice, may weaken or shift geographically, affecting billions of people in Asia, Africa, and the Americas. Flooding, drought, and altered precipitation patterns will change agricultural productivity and water availability. River systems once stabilized by glacial input may become erratic, with initial surges followed by long-term declines, stressing human and ecological communities alike. Storm intensity may increase as warmer oceans provide additional energy, leading to stronger cyclones, typhoons, and hurricanes, which compound the societal challenges posed by rising seas and diminished freshwater. Ocean currents, intimately linked to the presence of ice, adjust to freshwater influx from melting glaciers and ice sheets. The North Atlantic and Southern Oceans, critical to thermohaline circulation, may experience weakened or redirected currents. This alters heat distribution across the globe, affecting regional climates far from polar regions. Upwelling zones that support nutrient-rich fisheries may decline, influencing both local ecosystems and global food security. Ocean stratification may intensify, reducing vertical mixing of oxygen and nutrients and affecting the productivity of phytoplankton, the foundation of marine food webs. The loss of ice thus radiates through the oceans, impacting life from microscopic organisms to apex predators and the human communities that rely on them. Terrestrial ecosystems face similarly profound transformations. Alpine and glacially fed regions experience loss of snowpack, altering soil moisture, river flow, and seasonal habitat availability. Species adapted to cold environments must migrate to higher elevations or face population decline. Wetlands, estuaries, and floodplains dependent on glacial runoff experience reduced water availability and increased salinity, affecting birds, amphibians, and fish populations. Boreal forests encroach into tundra zones as temperature and moisture regimes change, while vegetation shifts in mid-latitude regions alter carbon storage and ecosystem productivity. The interconnectedness of ice, water, and life ensures that these ecological adjustments occur across continents, producing a reorganization of habitats and species distributions over decades. Human societies must navigate the multifaceted consequences of ice loss. Coastal urban centers face rising seas, storm surges, and inundation, requiring protective infrastructure, adaptation, or relocation. Agricultural systems must adjust to irregular water supply and altered growing conditions, employing irrigation management, crop diversification, and water conservation strategies. Hydroelectric generation declines as glacier-fed rivers shrink, while thermal and nuclear energy systems contend with higher water temperatures. Political tensions may arise over shared water resources, migration, and food security, emphasizing the global interdependence that ice has historically moderated. Economies, infrastructure, and cultural practices are challenged by the pervasive influence of ice on societal stability. Geophysical consequences extend through the lithosphere. The removal of massive ice sheets reduces pressure on the crust, allowing post-glacial rebound that slowly lifts land previously compressed. This adjustment can destabilize fault systems, occasionally triggering earthquakes or volcanic activity in formerly suppressed regions. River systems and sediment deposition patterns adjust to altered hydrology, reshaping floodplains and deltas. Coastal morphology evolves in response to both land uplift and rising sea levels, creating complex, dynamic coastlines over centuries. Even the planet's rotational characteristics are subtly influenced by mass redistribution, revealing the profound structural role that ice plays in maintaining Earth's equilibrium. Polar marine ecosystems experience profound stress as ice-dependent habitats vanish. The Arctic loses platforms for hunting and breeding, affecting polar bears, walruses, seals, and seabirds. In Antarctica, diminishing ice shelves and retreating glaciers disrupt breeding grounds for penguins, seals, and seabirds. The collapse of sea ice reduces populations of algae that underpin krill abundance, cascading through the food web to whales and other predators. Ocean chemistry shifts due to freshwater influx and warming, influencing species composition, migration patterns, and productivity. Ice loss is not localized. Its disappearance reshapes marine ecosystems across latitudes, demonstrating the global implications of frozen water on life. Glacial meltwater affects freshwater systems worldwide. Initial surges from melting glaciers increase river flow temporarily, yet long-term reductions lead to diminished seasonal water availability. In Asia, rivers like the Ganges, Mekong, and Indus provide water for agriculture, energy, and consumption for hundreds of millions. Reduced glacial input destabilizes seasonal flow, stressing agriculture, hydroelectric production, and urban water supply. Similar patterns occur in South America, North America, and Europe, highlighting the universal importance of ice in regulating freshwater systems and sustaining human and ecological communities. As ice vanishes, reflection deepens on its centrality to Earth's balance. Ice regulates temperature, stores fresh water, stabilizes coastlines, and supports biodiversity across land and sea. Its disappearance triggers interconnected changes that cascade through climate, hydrology, ecosystems, and human society. Scientific observation through ice cores, satellites, and modeling reveals both the scale of these transformations and the interconnectedness of planetary systems. Understanding ice loss is essential not only for predicting environmental change, but also for planning adaptive strategies and appreciating the subtle yet immense role ice plays in sustaining global equilibrium. The narrative of a world without ice emphasizes the delicate interdependence of life, climate, and human activity. From the massive ice sheets of Antarctica and Greenland to the smallest glaciers and seasonal snowpack, frozen water governs hydrological cycles, influences atmospheric dynamics, and shapes ecosystems. The loss of ice is not an isolated event. It is a global phenomenon with far-reaching consequences. Coastal zones are reshaped, oceans redistributed, freshwater supplies diminished, and climates altered. Biodiversity faces profound challenges, and human societies must adapt to changing resources, infrastructure needs, and environmental pressures. Observing these changes fosters a sense of both awe and responsibility, highlighting the intricate balance that ice maintains in the functioning of the planet. In coastal regions worldwide, rising seas reshape landscapes and human habitation. Low-lying deltas, such as the Ganges-Brahmaputra, Mekong, and Nile, face partial or complete submersion, threatening millions of residents. Saltwater intrusion alters soil composition, impacting agriculture and freshwater aquifers. In island nations, entire territories risk disappearance, necessitating relocation and the re-establishment of communities elsewhere. The socio-economic consequences are profound, encompassing displacement, loss of livelihoods, and cultural upheaval. Urban planning, disaster preparedness, and international cooperation must evolve to address these challenges, highlighting the inextricable link between ice and societal stability. Agricultural systems undergo widespread adjustment. Regions that historically relied on glacial meltwater for irrigation face variability in water supply. Crops such as rice, wheat, and maize may encounter drought or erratic flooding, requiring shifts in planting schedules, irrigation strategies, and crop varieties. In some areas, food security may be compromised, particularly for populations with limited adaptive capacity. Hydrological modeling and water management strategies become essential tools for governments and communities, emphasizing the crucial role that ice historically played in moderating seasonal water availability and sustaining agricultural productivity. Mountain ecosystems reveal subtle but consequential transformations. As glaciers retreat, New lakes form in valleys once occupied by ice, presenting both opportunities and risks. These glacial lakes can provide freshwater resources, but also carry the danger of sudden outburst floods that threaten downstream communities and infrastructure. Alpine flora, which depends on meltwater and specific thermal conditions, migrates upward, while fauna follows suitable habitats or face population decline. Over decades and centuries, these ecological shifts reorganize alpine biodiversity, demonstrating the long-term impact of ice loss on regional ecosystems and species distributions. Polar regions continue to experience dramatic ecological change. In the Arctic, declining sea ice reduces habitat for apex predators such as polar bears and diminishes hunting grounds for seals. Marine algae that grow on the underside of sea ice, a foundational element of the food web, decline, impacting krill populations and cascading through higher trophic levels. In Antarctica, retreating ice shelves accelerate glacier flow into the ocean, reducing breeding grounds for penguins and affecting nutrient distribution in surrounding waters. The polar response illustrates the interconnected nature of ice, ocean productivity, and wildlife survival, emphasizing that even distant human societies are affected by these shifts. Hydrological systems, closely tied to ice, demonstrate both temporal variability and long-term decline. Glacial runoff initially increases river flow, potentially causing flooding before decreasing as ice reserves shrink. Water storage and distribution for agriculture, hydropower, and urban needs become increasingly uncertain. Major river systems in Asia, South America, and North America, once buffered by glaciers, face diminished flow and altered seasonal patterns. Such variability necessitates advanced water management, infrastructure adaptation, and international collaboration to prevent conflicts and ensure sustainable water availability for ecosystems and human populations alike. Societal adaptation strategies evolve in response to ice loss. Coastal cities invest in levees, seawalls, and flood control systems, while considering relocation for highly vulnerable areas. Agricultural practices adapt through improved irrigation efficiency, diversification of crop varieties, and changes in planting schedules to accommodate altered water availability. Energy systems diversify to compensate for reduced hydroelectric potential, while urban planning incorporates climate resilience in infrastructure design. Policy, governance, and international cooperation are critical in managing the cascading impacts of ice loss, highlighting that human society is deeply intertwined with frozen water's regulatory functions. Climate systems continue to adjust to the absence of ice. Altered atmospheric and oceanic circulation patterns influence temperature, precipitation, and storm behavior globally. Monsoon systems shift, potentially weakening in some regions while intensifying in others, affecting billions of people. Thermohaline circulation slows or reroutes, redistributing heat and nutrients throughout the oceans, with effects on both ecosystems and human activities. Polar amplification increases regional warming in high latitudes, while feedback loops from diminished albedo and greenhouse gas release accelerate global temperature rise. The dynamic interplay between ice, atmosphere, and oceans demonstrates the far-reaching and interconnected consequences of ice loss. Marine ecosystems, sensitive to temperature, salinity, and nutrient availability, face ongoing stress. Phytoplankton populations, foundational to the oceanic food web, shift geographically and seasonally in response to altered conditions. Fish populations migrate to cooler waters or decline, affecting fisheries and food security. Marine mammals and seabirds adjust feeding patterns or experience population declines. Coral reefs, threatened by thermal stress and acidification, suffer bleaching and mortality, further reducing biodiversity. Ice loss exemplifies how changes in one component of the Earth system ripple through global ecosystems, reshaping life both above and below the waterline. As the narrative approaches its reflective conclusion, the broader significance of ice becomes evident. Frozen water regulates climate, stabilizes oceans, sustains biodiversity, and ensures predictable freshwater flow. Its disappearance triggers a chain of cascading effects across ecological, climatic, and human systems. Observation through scientific methods, including ice cores, satellite monitoring, and climate modeling, allows comprehension of these processes, revealing both immediate and long-term consequences. Understanding ice loss fosters awareness of the delicate balance sustaining planetary function and highlights the challenges and responsibilities facing humanity. Ultimately, a world without ice is transformed in fundamental ways. Sea levels rise, reshaping coastlines and inundating populated areas. River systems fluctuate, altering agriculture, energy generation, and freshwater availability. Polar and mountain ecosystems reorganize, affecting species, survival, and distribution. Ocean currents and climate patterns shift, influencing weather, productivity, and ecological stability globally. Human societies must adapt, employing engineering, policy, and resource management strategies to mitigate impacts. In quiet reflection, one appreciates the immense influence of ice on the stability of life and the planet, and the profound interconnectedness of natural and human systems that it regulates. As ice continues to vanish, feedback between climate, water, and ecosystems becomes increasingly pronounced. The cryosphere, once a stable regulator, loses its capacity to buffer seasonal and annual variability, altering hydrological cycles globally. Rivers that once relied on slow glacial melt now experience abrupt surges during warmer months, leading to episodic flooding followed by prolonged droughts. In North America, the Columbia, Colorado, and Yukon rivers illustrate this pattern, initially swelling as glaciers retreat, then diminishing as ice reserves wane. In South America, the Amazon's Andean tributaries face shifts in flow, affecting agriculture, hydroelectric dams, and local biodiversity. Across Europe, the Po, Rhone, and Rhine demonstrate similar hydrological disruptions, revealing that the disappearance of ice destabilizes freshwater systems on every continent. The oceans respond to these influxes of fresh water in complex ways. Thermohaline circulation, driven by density gradients formed by temperature and salinity, slows as glacial melt dilutes seawater. In the North Atlantic, the weakening of the Gulf Stream reduces heat transport to Europe, potentially cooling regions despite the global warming trend. Simultaneously, in the Southern Ocean, Antarctic meltwater alters currents that connect multiple ocean basins, affecting nutrient distribution and marine productivity. Upwelling zones, critical for supporting fisheries, are disrupted, impacting global food chains. Phytoplankton populations shift geographically, creating ripple effects throughout marine ecosystems, affecting fish, seabirds, and marine mammals. Ice, while distant from tropical waters, exerts an influence that reaches across every ocean basin. Terrestrial ecosystems respond in tandem. Alpine regions, newly exposed by retreating glaciers, develop nascent soils slowly enriched by sediment, dust, and decaying organic matter. Vegetation colonizes these areas, initially sparse, gradually forming complex plant communities. Fauna, ranging from insects to mammals, migrate upward or adapt to new microclimates, restructuring mountain biodiversity. Tundra and boreal regions experience shrub and tree encroachment as warmer temperatures and longer growing seasons allow species to expand. Wetlands dependent on glacial runoff shrink, affecting amphibians, birds, and fish. Soil erosion increases in areas previously stabilized by ice and snowpack, while sediment loads in rivers fluctuate, influencing deltaic environments and coastal stability. Human societies confront escalating challenges as water availability becomes unpredictable. Agriculture faces both excess and scarcity, with irrigation schedules disrupted by seasonal flow variability. Hydroelectric power, reliant on steady glacial runoff, becomes less predictable, prompting energy diversification. Urban centers along rivers and coastlines invest in adaptive infrastructure, including levees, floodwalls, and reservoirs. Yet the scale of potential inundation surpasses manageable limits in some regions. Coastal relocation becomes necessary for communities in deltas and island nations, with implications for cultural heritage, economic stability, and social cohesion. Governance and international cooperation are critical in addressing shared water and resource pressures, demonstrating that ice plays a central role not only in natural systems, but in political and societal equilibrium. Polar ecosystems continue to experience profound disruption. In the Arctic, the disappearance of sea ice eliminates hunting grounds for apex predators like polar bears and walruses, while affecting migration patterns for birds dependent on ice-adjacent feeding grounds. Ice algae, foundational to krill populations, decline, influencing whales, penguins, and fish species. In Antarctica, melting ice shelves accelerate glacier flow into the ocean, reducing breeding grounds for penguins and seals, while altering nutrient cycles in surrounding waters. These polar transformations are not isolated. Their effects cascade through ocean currents, climate systems, and global ecological networks. Climate feedbacks further compound these changes. As ice disappears, albedo declines, absorbing more solar radiation and increasing regional and global temperatures. Thawing permafrost releases additional greenhouse gases, including carbon dioxide and methane, reinforcing warming trends. Altered temperature gradients modify atmospheric circulation, changing storm intensity, precipitation patterns, and jet stream behavior. Monsoon systems shift geographically, affecting billions of people dependent on predictable rainfall. Ocean stratification alters, reducing vertical mixing of nutrients and oxygen, impacting marine productivity. Each of these changes interacts with others, producing complex, non-linear dynamics that ripple across the planet. Societal adaptation becomes increasingly complex and multidimensional. Water management strategies include reservoir construction, irrigation efficiency improvements, and policies for equitable distribution. Coastal cities implement flood defenses and consider planned relocation for vulnerable populations. Agriculture adapts through crop diversification, drought-resistant varieties, and altered planting schedules. Energy systems integrate renewable sources and adjust to variable hydroelectric output. International governance frameworks address shared river basins, migration pressures, and disaster response coordination. The loss of ice underscores humanity's reliance on natural systems for climate regulation, water supply, and food security. Geophysical consequences persist over centuries. Post-glacial rebound lifts land previously compressed by kilometers of ice, subtly altering topography and regional stability. Tectonic adjustments occur as pressure is redistributed, occasionally triggering earthquakes or volcanic activity. River courses shift, sediment deposition patterns change, and coastal morphologies evolve as some land rises and others are inundated. Earth's rotation and gravitational field experience minor, measurable changes due to mass redistribution. Ice, once thought inert, proves to be a structural regulator, integral to the planet's dynamic equilibrium. In reflection, the disappearance of ice illuminates its centrality to Earth's balance. Frozen water regulates climate, stabilizes oceans, sustains biodiversity, and ensures reliable freshwater supplies. Its loss triggers cascading effects across climate systems, ecosystems, and human societies. Observation through ice cores, satellites, and modeling allows humans to understand these processes, yet the physical transformations unfold independently, reminding us of the profound influence of ice on planetary function. Quiet contemplation reveals both the fragility and resilience of life adapting to these changes, underscoring the importance of preserving and understanding this critical component of the Earth system. Ultimately, a world without ice represents a fundamental transformation of Earth's physical and ecological processes. Sea levels rise, inundating coastal regions and reshaping shorelines. Rivers fluctuate, impacting agriculture, energy, and freshwater access. Polar and alpine ecosystems reorganize, altering species distributions and biodiversity. Ocean currents and climate patterns shift, affecting weather, marine productivity, and planetary heat balance. Human societies must adapt across multiple sectors, from infrastructure and agriculture to energy and governance. Observing these changes fosters awareness of ice's role in sustaining the delicate equilibrium that supports life and civilization. In the quiet of reflection, the scale of these transformations underscores the interconnectedness of climate, ecology, and human society, and the central place of ice within this intricate system. In tropical mountain regions, smaller glaciers play a subtle yet crucial role. The high-altitude glaciers of the Himalayas, for instance, feed rivers such as the Ganges, Brahmaputra, and Indus. These rivers support hundreds of millions of people with water for drinking, irrigation, and hydropower. As glaciers retreat, seasonal flow becomes irregular. Initially, meltwater increases river volume, causing floods and erosion. Yet long-term depletion leads to severe water scarcity during dry months. The impacts ripple through agriculture, energy production, and urban water supply, demonstrating that even ice distant from coastlines governs vital human and ecological systems. Similar patterns are observed in the Andes, where glacial melt supports communities and ecosystems in Peru, Bolivia, and Chile, and in the East African mountains, where seasonal ice contributes to rivers feeding lakes and farmland. River deltas, long-shaped and stabilized by sediment from glacial meltwater, face complex changes. In the Mekong, Ganges, Brahmaputra, and Nile deltas, rising sea levels interact with diminishing freshwater flow, leading to saltwater intrusion and soil degradation. Agriculture is directly affected, as crops sensitive to salinity struggle, and groundwater becomes brackish. Coastal wetlands, mangroves, and estuaries are submerged or degraded, reducing habitats for fish, birds, and invertebrates. These regions, densely populated and economically vital, illustrate how ice loss in distant highlands and polar regions can cascade into consequences thousands of kilometers away, affecting both human livelihoods and ecological networks. As glaciers retreat globally, glacial lakes proliferate, creating both opportunities and risks. Newly formed lakes store fresh water, potentially offering resource benefits to nearby communities. However, their instability carries the danger of glacial lake outburst floods, which can devastate downstream settlements, infrastructure, and agriculture. Monitoring and mitigation efforts become essential in regions with high glacial lake density. The Himalayas, Andes, and Alps contain hundreds of such lakes, highlighting the direct human consequences of glacial retreat, while also illustrating nature's reconfiguration of landscapes as ice disappears. The atmosphere responds dynamically to the loss of ice. Polar amplification accelerates warming at high latitudes, while diminishing albedo allows more solar radiation to heat exposed land and ocean surfaces. Temperature gradients between the poles and equator decrease, subtly altering jet streams and storm tracks. Monsoon patterns in South and Southeast Asia, as well as in Africa, experience shifts in timing and intensity. Droughts, flooding, and unpredictable precipitation cycles challenge agriculture, water management, and urban planning. Ice, once a stabilizing element, thus governs not only local climate, but also global atmospheric patterns critical to human and ecological systems. Marine ecosystems adjust to changing ice conditions with profound consequences. Sea ice reduction impacts primary productivity by limiting the habitat for algae that form the base of the food web. In the Arctic, krill populations decline, affecting seals, whales, and seabirds dependent on these resources. Antarctic marine life experiences similar cascading effects. Ocean warming, stratification, and altered salinity distributions further stress species, leading to shifts in populations and migration patterns. Fisheries, dependent on consistent productivity, face decreased yields or relocations of stock, illustrating how ice loss directly and indirectly shapes global food systems. Terrestrial ecosystems are not insulated from these changes. Alpine meadows and tundra zones, previously stabilized by seasonal snow and glacial meltwater, undergo rapid ecological shifts. Vegetation migrates upward or poleward in response to warming and changing water availability. Species that cannot adapt face population decline or local extinction. Wetlands, rivers, and floodplains, once nourished by predictable meltwater, fluctuate more unpredictably, affecting amphibians, birds, and fish. Boreal forests encroach on tundra regions as climate warms, altering carbon storage and ecosystem structure. Ice functions as a regulator of habitat, hydrology, and seasonal timing. Its absence reconfigures terrestrial ecosystems across continents. Human adaptation becomes an increasingly multifaceted endeavor. Water management evolves with infrastructure for storage, distribution, and flood control. Agriculture adapts through crop diversification, drought-resistant varieties, and improved irrigation practices. Urban centers in flood-prone areas invest in levees, flood walls, and resilient design, while some communities consider relocation. Energy systems adjust to the variable flow of hydroelectric sources, supplementing with renewables and storage solutions. International cooperation becomes essential for managing shared water resources. preventing conflicts, and mitigating cross-border impacts of ice loss. Ice, once taken for granted, proves to be central to human societal stability. Geophysical processes continue to respond to mass redistribution. Post-glacial rebound elevates formerly ice-covered land, altering local topography and influencing rivers, lakes, and coastal zones. Tectonic stresses adjust in response to pressure release, sometimes triggering seismic or volcanic activity. Sediment transport in rivers evolves as glacial inputs decline, modifying deltas and estuarine systems. Coastal morphology changes with rising seas and shifting land levels, demonstrating the interconnected nature of ice, lithosphere, and hydrosphere. Even the planet's rotation and gravitational field experience subtle adjustments, illustrating that ice contributes to Earth's structural equilibrium as well as its environmental balance. Reflection on these cumulative effects emphasizes the profound influence of ice on planetary systems. Frozen water moderates temperature, stabilizes oceanic and atmospheric circulation, sustains freshwater and ecosystems, and governs geophysical processes. Its disappearance triggers complex, interdependent responses across every domain, from polar ecology to tropical agriculture, from river hydrology to global climate systems. Scientific monitoring through ice cores, satellite observations, and climate modeling reveals both immediate and long-term consequences, allowing humans to anticipate, adapt, and understand the scope of transformation induced by ice loss. The story of ice, its presence and absence, illustrates the delicate balance sustaining life and human civilization. As glaciers, ice sheets, and sea ice vanish, they reshape oceans, continents, and climates. Ecosystems reorganize, species migrate or decline, and humans adapt to altered resources, infrastructure, and environmental conditions. Observing these processes underscores the interconnectedness of planetary systems and the subtle yet profound role that ice plays in regulating life. In contemplating a world without ice, one perceives both the vulnerability of natural systems and the resilience inherent in life, and appreciates the centrality of ice in maintaining the stability that sustains the planet. In regions dependent on snowmelt and glacial runoff, water scarcity gradually becomes the norm. The Andes, home to tropical glaciers, feeding rivers that sustain agriculture and human settlements, witness reduced stream flow during dry months. Communities that once relied on consistent water availability are forced to modify irrigation schedules, ration drinking water, and explore alternative sources. Reservoirs, once predictable, experience fluctuating levels, complicating hydroelectric generation. In Asia, Himalayan meltwater that sustains the Ganges and Indus basins undergoes similar seasonal volatility, affecting hundreds of millions of people. The cumulative effect is a redefinition of water security across continents, illustrating the central role that ice has historically played in stabilizing freshwater resources. Deltaic regions, particularly low-lying coastal plains, confront simultaneous pressures from rising seas and altered sediment flow. In the Ganges Brahmaputra Delta, sea level rise accelerates coastal inundation, while reduced river flow diminishes natural sediment deposition, leading to land loss and increased salinity. The Mekong Delta experiences similar dynamics, with impacts on rice cultivation, aquaculture, and rural livelihoods. In the Nile Delta, reduced flow from glacial-fed tributaries, combined with sea level rise challenges, the balance of freshwater and salinity, threatening food production and urban water supply. These changes underscore how the disappearance of ice, far upstream, can reverberate to the very edges of continents, affecting ecosystems and societies alike. Glacial lakes, formed from retreating ice, present a combination of resource potential and hazard. These lakes temporarily store fresh water, offering supplemental water for human use and ecosystem maintenance. However, many are prone to sudden outburst floods, particularly where moraines formed by glacial debris act as natural dams. In the Himalayas, Andes, and Alps, monitoring and mitigation become essential to prevent catastrophic downstream impacts on communities, agriculture, and infrastructure. The emergence of these lakes exemplifies nature's dynamic reconfiguration following ice loss, highlighting the duality of opportunity and risk inherent in changing landscapes. Polar ecosystems continue to shift as ice disappears. In the Arctic, declining sea ice diminishes habitat for polar bears, walruses, seals, and seabirds, while affecting the timing and availability of food resources. Ice algae, which grow on the underside of sea ice and underpin krill populations, decline, causing ripple effects up the food chain to whales, penguins, and other predators. In Antarctica, the collapse of ice shelves and accelerated glacier flow reshape coastal ecosystems, affecting penguin colonies, seal populations, and marine nutrient distribution. These polar transformations illustrate the global interconnectedness of ice, ocean systems, and climate, emphasizing that even distant human societies feel the consequences. Mountain ecosystems adapt to rapidly changing conditions. As glaciers retreat, newly exposed rock and soil gradually develop vegetation, initially sparse, but eventually forming complex plant communities. Animals migrate, adapt, or face population decline in response to altered water availability and habitat. Alpine streams, formerly fed consistently by glaciers, experience seasonal variation in flow, influencing aquatic species and downstream ecosystems. Wetlands and floodplains, reliant on meltwater, shrink or dry, altering habitat availability for amphibians, birds, and fish. These shifts illustrate that ice functions as both regulator and reservoir, and its loss reshapes landscapes, water flow, and ecological interactions across altitudes. Human societies implement layered adaptation strategies. Urban areas invest in flood defenses, coastal reinforcement, and relocation where necessary. Agriculture evolves with irrigation efficiency improvements, crop diversification, and seasonal adjustments to planting and harvest cycles. Hydroelectric systems adjust to fluctuating river flows, integrating alternative energy sources where feasible. International collaboration addresses shared water resources, disaster preparedness, and food security, demonstrating that ice loss is not merely an environmental concern, but a multidimensional societal challenge. Ice thus acts as both a natural regulator and a stabilizing influence on human civilization. Climate systems respond dynamically to ice loss. Reduced albedo from melting surfaces accelerates regional warming, particularly in high latitudes. Atmospheric circulation patterns adjust, influencing storm tracks, precipitation timing, and intensity worldwide. Monsoons, critical to billions of people, shift or weaken, producing droughts in some regions and flooding in others. Ocean currents adjust to freshwater influx, modifying heat and nutrient distribution. Stratification intensifies, reducing vertical mixing of nutrients and oxygen, affecting primary productivity and food webs. Ice, though often distant from populated regions, shapes climate, water cycles, and ecological productivity across the globe. Marine ecosystems experience ongoing transformation. Sea ice retreat reduces primary productivity by eliminating habitats for algae, which form the base of polar food webs. Fish populations migrate to maintain suitable conditions, affecting commercial fisheries and local subsistence. Marine mammals and seabirds adjust feeding patterns or experience population decline. Coral reefs and tropical marine systems, sensitive to temperature and acidification, face additional stress as ice regulated ocean currents shift heat and nutrient distribution. These interconnected effects demonstrate that ice loss reverberates from polar to tropical regions, affecting biodiversity, ecosystem function, and human reliance on ocean resources. Terrestrial ecosystems gradually reorganize in response to climate shifts and altered water availability. Alpine, tundra, and boreal regions see vegetation migration and shifts in species composition. Soil moisture, influenced by changing snowpack and meltwater, alters plant growth and carbon sequestration patterns. Wetlands and riverine ecosystems fluctuate unpredictably, affecting species reliant on stable hydrological conditions. Forest boundaries shift, tree lines ascend, and shrub encroachment transforms previously open tundra landscapes. The loss of ice, once a stabilizing influence on seasonality and water flow, results in the slow but inexorable reconfiguration of terrestrial habitats. Ultimately, reflecting on a world without ice reveals the profound interconnectedness of Earth's systems. Frozen water regulates climate, stabilizes oceans, supports biodiversity, and ensures predictable freshwater availability. Its disappearance triggers cascading changes across hydrological, ecological, and societal domains. Scientific observation through ice cores, satellite monitoring, and modeling allows humans to understand these processes, anticipate consequences, and develop adaptive strategies. Quiet contemplation of these transformations fosters awareness of the subtle yet critical role ice plays in sustaining the balance and habitability of the planet. In a planet devoid of ice, coastlines are redefined, rivers fluctuate, and climates shift. Polar and mountain ecosystems reorganize, marine and terrestrial species adjust or decline, and human societies adapt to altered resources and environmental pressures. Ice, often distant from daily human experience, proves central to regulating the Earth system. Observing the scope of change encourages a reflective understanding of interconnectedness, resilience, and vulnerability. The disappearance of ice is both a challenge and a profound lesson, emphasizing the delicate balance that sustains life, the importance of foresight and adaptation, and the quiet yet immense influence of frozen water on our world. As the planet adjusts to the absence of ice, coastal zones illustrate the tangible effects of rising seas. Cities like New York, Mumbai, Shanghai, and Jakarta face inundation risks, prompting the construction of levees, seawalls, and flood defenses. Low-lying island nations experience existential threats, with relocation and international resettlement becoming critical considerations. Mangrove forests, salt marshes, and coastal wetlands, natural buffers against storm surges, are submerged or degraded, altering habitats for fish, birds, and invertebrates. Human settlements must adapt to these shifting landscapes, balancing infrastructure, community, and ecosystem needs in the absence of ice-driven stability. In mountain regions, glacial retreat reshapes both ecosystems and human use of water resources. Alpine streams, initially swollen by melting glaciers, later decline, affecting hydropower generation, irrigation, and potable water supply. Soil stabilization decreases as snowpack and ice vanish, increasing susceptibility to landslides and erosion. Flora migrates to higher elevations, while fauna follows suitable microclimates or face population decline. The delicate timing of seasonal water release, once regulated by ice, is disrupted, demonstrating the intimate link between frozen water and ecological resilience. River systems around the globe illustrate the pervasive influence of ice. The Indus, Ganges, Mekong, Columbia, and Rhine, among others, experience fluctuating flow patterns that impact agriculture, energy, and urban water supplies. Glacial meltwater, once a stabilizing seasonal reservoir, now provides erratic input. Surges may cause flooding, while subsequent shortages stress ecosystems and human settlements. Reservoir management becomes critical, requiring advanced monitoring and policy interventions. Ice, though distant from most human experience, governs freshwater stability across continents, underpinning agriculture, energy, and urban development. Marine systems continue to adjust in response to ice loss. Sea ice retreat diminishes habitats for polar algae and krill, disrupting food webs that support fish, seabirds, and marine mammals. Coral reefs, sensitive to temperature and nutrient changes, experience bleaching and mortality. Ocean circulation, influenced by glacial meltwater, redistributes heat and nutrients, altering productivity and species composition across latitudes. Fisheries are affected by both shifting stocks and declining productivity, highlighting the interconnection between ice, oceans, and human sustenance. The disappearance of ice thus reverberates from polar seas to equatorial oceans, shaping life and livelihoods globally. Atmospheric circulation patterns evolve with diminishing ice coverage. Polar amplification raises high latitude temperatures, while reduced albedo accelerates global warming. Jet streams and storm tracks shift, affecting weather patterns in distant regions. Monsoon intensity and timing change, influencing agriculture, water supply, and ecosystem health for billions of people. Extreme weather events, including hurricanes, cyclones, and heavy precipitation, may increase in frequency or intensity, demonstrating that ice loss interacts with both the atmosphere and hydrosphere to produce far-reaching consequences. Societal adaptation continues to unfold in response to these challenges. Urban centers enhance flood defenses, integrate climate resilience into infrastructure, and plan for potential relocation. Agricultural systems adopt drought-tolerant crops, diversify planting schedules, and implement water-efficient irrigation practices. Hydroelectric systems adjust to fluctuating flows, supplemented by renewable and alternative energy sources. International collaboration focuses on shared river basins, disaster response, and equitable resource management. The loss of ice illustrates the dependence of human society on natural regulation and the necessity of proactive adaptation to maintain stability and well-being. Ecosystems, both terrestrial and marine, continue to reconfigure in response to altered hydrology, temperature, and habitat availability. Alpine, boreal, and tundra ecosystems shift as vegetation migrates and species adapt or decline. Wetlands and floodplains fluctuate unpredictably, affecting amphibians, birds, and aquatic species. Ocean productivity changes as primary producers respond to altered nutrient and temperature regimes, cascading through marine food webs. Ice, once a stabilizing and buffering force, functions as a keystone in ecological balance, and its absence triggers widespread reorganization of habitats and species distributions. Geophysical processes remain ongoing over centuries. Post-glacial rebound elevates land previously compressed by ice, influencing rivers, lakes, and coastal zones. Tectonic adjustments respond to pressure redistribution, occasionally triggering earthquakes or volcanic activity. Sediment transport and deposition patterns evolve in response to changing hydrology. Coastal morphology transforms with rising seas and land elevation shifts, altering habitats and human settlements. Even the Earth's rotation and gravitational distribution are subtly affected by mass redistribution. Ice exerts structural influence over the planet, highlighting its integral role beyond climate regulation. In quiet reflection, the absence of ice underscores the interconnectedness of Earth's systems. Frozen water moderates climate, stabilizes oceans, sustains biodiversity, and ensures predictable freshwater availability. Its disappearance triggers cascading effects across ecosystems, hydrology, and human society. Scientific observation through ice cores, satellites, and modeling allows humanity to comprehend these changes, anticipate challenges, and implement adaptive strategies. Understanding ice loss illuminates the fragility and resilience inherent in planetary systems and emphasizes the subtle yet profound influence frozen water exerts on global equilibrium. Ultimately, a world without ice represents a fundamental transformation of Earth. Coastlines are reshaped, river systems fluctuate, climates shift, and ecosystems reorganize. Marine and terrestrial species adjust, migrate, or decline. Human societies adapt through infrastructure, agriculture, energy, and governance measures. Ice, often distant from daily human life, emerges as a central regulator of planetary stability. In calm contemplation, the scope of these changes highlights the interdependence of natural and human systems, the delicate balance sustaining life, and the quiet, immense influence of ice on the world we inhabit.